We just said that one of the generalization or one of the result that we obtain when we go to higher order, or if you like, a more accurate description of of flame dynamics, is to use the flame speed relation, which is described here, which include the effect of stretch modulated by this Markstein length. Now, let me clarify that the flame speed, it's a local property. In other words, it's the speed that this point here propagates against the flow. And this point propagates against the flow at a different velocity because the local stretch is different here than here, and so on, okay? Which is different than the assumption that we did before, that at all points is the same. The first thing I would like to do is just to explain what is flame stretch and what is the Markstein length. In other words, to obtain expression for these things. And so flame stretch, we have defined it before as the fractional area change that result when the flame propagate, namely 1 over a dA dt. Now this is good. We have seen that we can compute this right away for simple configuration, but what if the flame is highly curved and multidimensional? Then what we have to do is to look at an area like the blue area here and ask, after a small short distance, small time delta t, how did this area got distorted as a result of the propagation and the fact that there is a flow field that changed from time t to delta t. And when we do this, we obtain a relation for flame stretch. And there are few such relations that are all equivalent. One of them is described here, which says that the flame stretch is curvature, okay? Now, curvature is kappa. The curvature of a surface can be computed from computing the divergence of the unit normal. Actually, it's really twice the mean curvature, but it's used, the term curvature is used for that. And it's equivalent, by the way, to the fact that, that kappa is equal to the sum of the two principal, the reciprocal of the two principal radii of curvature. So for example, if you have a sphere, because of the symmetry in all direction that you will cut the sphere, it will have a radius of r. And so both principal radii of curvature is going to be the radius r, and so curvature is 2 over r, okay? But if you have a cylinder, let's say, if you cut it horizontally, you get a radius of curvature r, the radius of the cylinder. If you cut it vertically, you get essentially a flat surface which has an infinite radius of curvature. And so for a cylinder, the two principal radii of curvature is infinity and r, okay? And for other surfaces, it will have, you know, different, of course, behavior. And it's, again, that's a local property. It's a property at a given point. And so it can be computed this way, as I said. So this is one effect. So for example, in a spherical flame, that was the main effect. And I'm going to show you, again, those two special cases in a minute. The other one is the strain rate Ks. Ks, S stands for strain. So this is the strain that the flame experiences. In other words, if you take the strain rate tensor, you dot it with a normal on both sides, you can compute the strain. Of course, the strain rate needs to be evaluated at the flame. Okay, so here is the strain rate. So those combination, of course, give you the stretch. And the units are the same, as I said, 1 over second. Strain rate have units of 1 over second. Curvature have units of 1 over centimeter. You multiply by centimeter per second, you get 1 over second. So it has all, the two terms have the same units of 1 over second. another way to write, or another expression from flame stretch, I will start with this one, which is really equivalent to this, but it's a bit more, one can more clarify it. It has the curvature multiplied by the propagation velocity plus the divergence of the tangential velocity, which is essentially, it's like the gradient along the surface, okay? So this is another way of putting it. Now, the two are equivalent because you see the strain rate, which is the last two terms in this expression, can be decomposed into a normal and tangential component. The normal component of the strain is proportional to kappa, which is the curvature, and the tangential part is exactly the gradient along the surface. And so you can see from this pictures here, for example, that normal straining depend on the curvature, and they would, if the curvature is negative, right, they cause, as a result of the straining, a positive stretch. Whereas if the curvature was negative, they cause a negative stretch because the surface gets compressed rather than stretched. Whereas the tangential part here depends if the gradient are positive inward or positive outward, right? And so it's really independent of curvature. It depends only on the gradient on the surface. So in this case, the flame is compressed. In this case, it is positively stretched, okay? So you see that, my point is that the strain rate has a normal as well as tangential component, and so as a result, those two expressions are the same because there's a normal component here that added to this to give this, and the remaining is the other one. So they are equivalent. And sometimes it's more convenient to use one, or sometimes it's more convenient to use the other. Let's say if you take the spherical expanding flame, we have seen from first principle that the stretch was 2r dot over r. If you use, let's say, the relation that I wrote last, it has Vf kappa plus, remember, it was the velocity tangential to the surface. But the spherical flame, the velocity are normal to the surface. They are in the radial direction. So there is no contribution from this term. This term gives you 0 in that case. And so the stretch is going to be the propagation velocity, which is r dot, multiplied by the curvature of a sphere, which is 2 over r. So that relation is immediately the same as that. If you evaluate the expression that I wrote here, well, then the total strain would have a normal component and a tangential component. The normal component gives you this expression, which when added to this, give you again 2r dot over r. So, of course, both relations are the same, and they all give you the same result. For a stagnation point flow, the expression that this expression is quite convenient because you see the flame is stationary, it's not propagating, so this is 0, and the tangential velocity is the v component along the surface, and that gives you immediately the strain rate to epsilon. Of course, you can compute it also from the other relation. It's a little bit more involved, but you can compute that as well. And of course, they are obtained, they give you the same answer as the one that we computed directly from the definition. So in all cases, you get the same answer. And again, remember that there are two effects, and the spherically expanding flame and the stagnation point flow are two prototype example of stretch, each representing a different part of stretch. One is due to the flow field or strain, the other one due to propagation. Okay, so, here is just an example that you can find it actually in my paper here of 83. If you just assume that the flame is a real cone and you write an expression for the cone, you can actually see that the stretch is negative. Okay? So a conical flame is negatively stretched, or it's compressed. Okay. So, and the two, by the way, radii of curvature in this case it's infinity and minus r over cosine alpha, because every segment here has, right, if you take a horizontal cut, then the radius of the radius of curvature is not r, but it depends on the angle alpha. It becomes smaller and smaller as you go up towards the apex. Okay, so again, to summarize, there are several ways to calculate stretch. They are all equivalent, and they all give the same answer for those simple questions that the simple examples that we have examined. The next item, or the next comment that I want to make before talking about Markstein length is that, remember I told you earlier that the flame speed is equivalent to a statement of an equation that describes the evolution of the flame, that if you want you call G, if I want I call F, whatever. And so here is the equation, but now instead of the flame speed SF, I wrote the flame speed with the Markstein correction, right? Before we had just SL times the gradient of F. So if you now substitute the fact that this K depends on the flow field, of course you get a quite complicated equation. I don't want to do anything more with that equation, just want to show you that it's a complicated equation and it's coupled to the flow field. So in fact you have to solve this in conjunction with the flow field, which is changing as a result of the fact that the flame is propagating, and so, okay. So this description, of course, of a flame of general surface propagating in a flow to compute the coupled effect require, for example, solving the Navier-Stokes equation, but also tracking that surface. And one way that this was done in some of our work, as well as some of Peter's work, is essentially using level set approach to track the flame surface. And in some cases, it's coupled to the flow field. Some people have just solved the equation without the coupling, whatever the case is. But this is the idea. Everything is behind, the ideas are behind this equation. Here are some example of the flow field, as I said, computed, and with the flame surface tracked by a level set. And this is the flow field of a Bunsen flame. In this case, the incoming flow is uniform. In this case, you can see that it's a Poiseuille flow, okay? In both cases, you see that the streamline are deflected as they should, okay? And note that the flame, the curvature caused this apex that before we did not resolve properly to be rounded, right? The tip of the flame. So this is just an example. This, well, I just spoke about this. This is actually another example that shows again a laminar flame which is corrugated. There is a periodicity assumed here in the transverse direction, and the burn gas, which is really didn't start here but much below this, is uniform. I'm sorry, not uniform. Is at rest, is a quiescent. In other words, this corrugated flame is propagating down. Okay, so the flow field is essentially far enough is zero. As a result of the propagation, as it propagates down, you see that the flame induce a flow field in the unburned gas, and the flow field is directed in such a way that it's going from those from the more flat region of the flame towards the troughs. So the flow is pointing this way, and by doing so, it maintains this cellular structure, which, by the way, is a result of a hydrodynamic instability, and that's why the flame can propagate in this steady fashion at some propagation speed, which is, of course, larger than the laminar flame speed. But we are going to discuss that later on. Okay, so now we said that the flame speed is affected by the stretch rate, and this is modulated by the Markstein length. Now, the Marsden lengths, the hydrodynamic theory provided an expression for it, and the expression depends on sigma, which is the density ratio. If you want, it's related to the heat release, right? The heat release affect the temperature change, and that affect the density change. So sigma is essentially dictated by the heat release. And then it depends on beta, the Zeldovich number, right, or the activation energy. And then it depends also on this Lewis number, which I called here an effective Lewis number. Because if you have a mixture of two components, fuel and oxidizer, then the effective Lewis number is given by an expression like this, where phi tilde is the deviation of, it's a deviation from one, is it? Yeah, it's a deviation from one of the equivalence ratio. In other words, it's equal to the reciprocal of phi minus 1 for lean mixture, and it's phi minus 1 for rich mixture. So phi tilde, it's always a positive quantity that show the deviation from 1. So you see, phi tilde is 0, which means that you're exactly at stoichiometry. Then the effective Lewis number, it's exactly the mean of the two Lewis number, okay? But as phi tilde become larger, in other words, if you move more towards the lean mixture, then you see that the fuel counts more heavily because phi tilde is larger than 1, so 1 is negligible, compare it, and then what you get is that in the limit that the effective Lewis number is that of the fuel. And if you move towards the rich mixture, the Lewis number is that effectively of the oxidizer, right? So it's always the deficient component which weight more in determining the effective Lewis number. Okay, so this is essentially the Lewis number. So the Lewis number, remember, measure the thermal diffusivity to the mass diffusivity, and Lewis number not equal to 1 means that that heat transferred away from the flame is transferred at a different rate than mass is diffusing towards the flame. And those differences, whether it's the gain is in the heat loss or the gain is in the mass that diffuse towards the flame, right, depending if it's less than 1 or bigger than 1, have an effect on the flame propagation. So, this is the Marsden length. Now, here are curves that show the theoretical expression that was derived for different fuels and how they behave. Note that, and this is the Marsden number, which means it's a Marsden length scaled with respect to the flame thickness. Remember that the Marsden number, Marsden length, it's a property that is proportional to the flame thickness. And so we see that the Marsden number, or Marsden length for that purpose, the same thing, decreases for the say the hydrocarbon or the alcohol fuel, but for hydrogen it increases as you increase equivalence ratio. In fact, it's even negative in that case, okay? And in the lean regime, and change to positive later on. Now, one can also write an expression for the Marsden length. In other words, the theory was developed in such a way that you can also account for for all the transport property to be temperature dependent. So if they are temperature dependent, then the previous term, which was simply sigma log sigma over sigma minus 1, is now a bit more involved the integral, which depend on what the law of the temperature dependent of conductivity. In particular, if lambda is 1, which means a constant property, the integral of 1 over c is log sigma, and that gives you exactly the previous relation, of course. The same thing with the second term. So really the only difference is just those coefficients, but the dependence on sigma and the Lewis number remain the same. Okay, so I will keep on going with this. People have often liked to write an expression for the flame speed relative to the burn gas. Now, in all the discussion so far, as I have pointed out earlier, I have defined the flame speed relative to the unburned gas. Now, Why is there a difference? Well, the difference is because, remember that we said that as a result of when you account for flame thickness not zero, namely if you account for effects which are of order delta, the mass flux in is not equal to the mass flux out, and there is a difference between them. So the velocities, if you relate the flame speed relative to the unburned or to the burn gas, there is a difference that comes from this order delta term. As a result, the Markstein lengths expressed in terms of the, or relative to the burn gas, will take on a slightly different form, but related. And you can easily see that there is a relation between this L superscript B and the L that I wrote before, but clearly they are not equal, okay? Now, another important comment is the one that is here. In the hydrodynamic description, the flame is an interface. The unburned gas is valid all the way to the flame surface, and then across it you have burned gas. But in the real description, including in the asymptotic description, but if you do it carefully, the flame has some thickness, okay? Now, when people talk about Markstein lengths, it depends at what position within the flame you are measuring it, computing it, and so on. And the same thing is in the asymptotic relation. It depends at what position within the flame zone you are expressing the velocity dependence on stretch. And that will make a difference because the Markstein length is of the order of the flame thickness. And so any distance within the flame thickness that you change will give you an order 1 difference in the Markstein length. And that comment is what I said here. The Markstein length is uniquely determined only in the asymptotic limit where the whole flame is treated as a surface that coincides with the reaction sheet and the flame speed evaluated at this location on the unburned side. Experimental measurements, on the other hand, are typically taken at specific reference location inside the flame zone. So to make meaningful comparison between the theory and experiment, the Markstein number must, and I emphasize must, be adjusted to properly calculating the gas velocity at the chosen reference location. That will cause, in general, a drop in the result that I have shown you before. In other words, the adjustment is usually a drop in that value. So the actual value are somewhat lower than the one that you see here. And in fact, in that paper, we show calculation of both this value as well as the adjusted value. But the main point here that you get lower value, and as a result, even for methane that you see here, it has a positive value, it could be negative, okay? So it depends where you measure it. And that's a very important point that it was recognized quite a while ago, but I don't think it has been fully comprehended in the literature. So occasionally one still see comment about that these are not equal or not the same or not compatible within the theory and so on. But this was already made more than 10 years ago in this paper followed by this one. Okay, so the last comment is that we have an expression for the flame speed, right? Here's the Markstein length, and then it's proportional to the flame thickness and stretch. What about the flame temperature? Well, the theory tells you that even the flame temperature vary from point to point along the surface. It's not equal to the adiabatic flame temperature all over. And the correction is also proportional to the Lewis number -1, with a coefficient here which is not the Markstein length, but it's something related to these integrals that you had before. So positive stretch will reduce the flame temperature if the Lewis number is bigger than 1, right? Because then this positive and this quantity is positive. And if the stretch is positive, it will reduce it. And it will increase the flame temperature if the Lewis number is less than 1. And the flame temperature is unaffected by stretch if the Lewis number is about or close to 1. On the other hand, for the flame speed, positive stretch increase or decrease the flame speed from the laminar flame speed, depending if the Lewis number is larger or smaller than a value which is not 1, but it's close to 1, and it's slightly on the negative side, which is this LE star, which can be calculated from here clearly. Roughly speaking, we can say that the flame speed decrease with stretch when Lewis number is greater than 1, but it's not exactly 1. That's the point. And one can see this trend in this experiment. For example, what is shown here is temperature for different strain rates, so it's for different stretch of methane air flame at near stoichiometry, and the Lewis number is approximately 1 for methane, and so the temperature is nearly a adiabatic temperature for any of the stretch for all strain rate. Now you don't quite see it in this graph because of course the position of the flame change with stretch, right? As this is a counterflow, and so as the flame gets stretched, as you increase the stretch, the flame gets closer and closer to the wall, okay, to the stagnation surface. So what Professor Law did was to superimpose all these curves such that they are at the same location, and you see then that the temperature is almost unaffected, including the flame temperature, unaffected by stretch. And these curves show exactly the trend that I spoke about with the flame speed, if it's positively stretched or negatively stretched, depending on stoichiometry, because on the equivalence ratio, because the equivalence ratio will change the importance or the effect of the Lewis number. Because of lack of time, I'll leave you read those from, I believe they are in the notes, so you can find them, and that's quite clear. So the last comment that I think, well, I don't know if it's the last one, we'll see. So this one is the expression, or an expression for a new expression, let's say, a revised expression for the propagation speed of a spherical flame, where we have taken into account the correction term, which is the order delta. Remember that delta here is going to be inversely proportional to the radius r, right? Because delta is the flame thickness divided by the radius of the flame. And so the correction has a term that depends on this burned Markstein length. And if you now graph the propagation speed as a function of position, you would obtain curves which looks like this is the red curve is the asymptotic value, the blue curve is the numerically computed one. Of course, they are good when the flame is sufficiently large. Otherwise, when the flame is small, you expect a deviation. The asymptotic solution, in fact, go here to infinity, and so it fails in this region, but the numerical solution will take you to r equal to 0, right? And if you compare this result with the experimental result that I have shown you before, you will see that, again, you have situation where the propagation speed increase towards the asymptote, and that happened, for example, in the rich limit, whereas in the lean limit, or the other way around, that happened in the lean limit, and in the rich cases, it's going to decrease towards the asymptote. And this fully agree with this is the asymptotic result, or it's based on the asymptotic formulation, and those are the experiment, and you see that they quite agree with each other. By the way, remember that these asymptote to sigma times r dot, right? Which I mentioned before, it's a way to measure the laminar flame speed. Of course, they asymptote to different level because for different equivalence ratio, sigma is different. The heat release is different, and so the value, the asymptote value is different. So that's clear. So I'm going to skip this one, and we're going to move to the next lecture, which is going to be no, sorry, I skipped too much. Okay, which is going to be on ignition and extinction phenomena. And I'm going to here also pick on some of the important things that I want to address and skip the others. And so this is a discussion that you can read later by yourself. I want to focus the same first thing on flame extinction, and I would re-examine a planar flame propagating into a quiescent mixture, but with volumetric heat losses. And so here you have the setup. In the lab flame, the flame is propagating towards a fresh mixture. In a coordinate system attached to the flame is stationary, and the incoming gas, it's coming at a speed s, and the speed s is clearly lower than the laminar flame speed as a result of heat losses. And so the question is to determine this s. So we know the laminar flame speed for this mixture, and we want to compute the propagation speed which result from heat losses. So we have some heat losses that are described here phenomenologically. The boundary conditions are clear, very similar to the previous problem that we have examined, which is summarized here. So we have here continuity, the energy equation, and the term here that describe heat loss. And the heat loss is a function of temperature. So for example, if it's conductive loss, it's going to be a heat loss parameter K multiplied by the difference between temperature T and the unburned temperature, or the fresh mixture of the fresh mixture. And if it's due to radiation, it's going to be something of the form T to the 4, say minus Tu to the 4. But at the moment, for this discussion, it doesn't matter which it is. It's some function of temperature, okay? And and then you have the equation for the mass fraction U. Okay, so now this is the problem, and the main question is to determine the profiles as well as the propagation speed s, okay, or the velocity s. Okay, so again, I'm going to use the idea that I have developed earlier, that I can treat the reaction zone as a sheet, across which the temperature and the mass fraction are continuous, that there's a relation between the fluxes, and that the flux of fuel is given by this expression. But remember that we have generalized it to be at a temperature Tf. In other words, the flame temperature is Tf, not a adiabatic temperature. Okay? We have generalized this to this. And I said that this can be derived systematically from first principle. But it's simpler to examine the problem in this framework because the algebra and the work is simpler. So the right-hand side here is equal to essentially the mass flux of an adiabatic flame multiplied by this exponential, which has the difference between the flame temperature and the adiabatic temperature. And the SL, the laminar flame speed, we have already derived before an expression for it, which I repeated here for the sake of completeness. So this is the problem that we want to solve, which, as you notice here, I have already set the reaction term to 0. And so this equation needs to be solved on the unburned gas and on the burned gas separately. So we non-dimensionalize them, and then basically, I'm going to skip the algebra and show you the result. So the solution show that here is the mass fraction, which is the blue curve, if you like, in the preheat zone and in the burn side. And note that since I am, in general, I didn't make any assumption about Lewis number here, so it's a general Lewis number, but it's a one reactant mixture. In other words, fuel lean or fuel rich, if you like. And then this little s is essentially the propagation speed normalized with respect to the laminar flame speed, okay? So, because remember the equations now are s dt dx. This rho u is equal to the, based on the condition at minus infinity, to the s, which is the propagation speed of the non-adiabatic flame. Okay, and the temperature is given by this expression, where on the unburned gas, very similar to before, it's an exponential, essentially, growth from Tu to the flame temperature. But in the burn side, as a result of the heat loss, we have a slight decrease, which is described on the scale as a linear decrease in temperature. So you see here it's a linear decrease. And this phi star is the deviation of the adiabatic temperature, of the flame temperature from the adiabatic temperature. So the key thing here is to compute the deviation of the flame speed from adiabatic, the phi star, and the propagation speed s. And if we apply all the conditions that we have across the flame, we get the following two relations. Where are they? Yeah, here. One of them is phi star equal to minus the log of s squared. And the second one is that s phi star is equal to 1 over s times a quantity that I called the total heat loss. The total heat loss is the integral from 1 to Ta, which means from the unburned side to the burn temperature of this function that include the heat loss function, right? Whether conductive or radiative, plus a contribution, that's the loss from the unburned, from the preheat zone, plus a contribution of the loss from of the heat loss from the burn side. That's why I call it the total heat loss, okay? And so, for example, if you use a conductive loss, which is G of t is proportional to t minus 1, and you integrate this equation, you get that the QL is 2 times K. K is the coefficient in front, okay? And for a more complicated law, you can integrate that and obtain what it is. So at any rate, there is a loss here. So now when you combine those two relations, you get the one in the box here, right? Because you replace the phi star with the S. So you replace the phi star with the S that you have here. And so you get S squared log S squared equal to minus QL. And QL is a well-known quantity that depends only on the law of the heat loss that you apply. And so now we want to analyze this, this expression. Now I didn't want to skip the previous slide. I just wanted to get to the answer and now discuss what that slide is. So in one of the previous slides, when I show you the solution, which is here, solution in the unburned gas, or in the burned gas, I said that there is a linear drop. Well, in principle, a linear drop is not acceptable because if you go sufficiently far, it's going to go negative. Temperature cannot go negative. The reason for that, it's because really this is not the complete description of the temperature on the burned gas. The complete description is this curve here, which is an exponential decay. The only problem is that on the scale that we have started with, well, the reason is, or the difference is that the temperature drop in the burn gas is extremely slow and can be described only on a scale of the order beta. And remember, beta is the activation energy, and it's a large number. So it very slowly decays to the cold value. And for the description of what's going on in the flame, it was sufficient to take only the linear part that described the behavior of this exponential decay near the flame. Okay, I just told you in words what we did in mathematics. So now let's go back to this expression. And if we graph it, if we plot S as a function of the heat loss, we get a curve that has a turning point at some point here, which is approximately, which is exactly 1 over E, which is about 0.37, okay? And this S is the propagation speed. Now remember that these quantities are dimensionless. So this S was scaled with respect to the laminar flame speed. That's why it's 1 when there is no heat loss, right? When there is no heat loss, the propagation speed is the laminar flame speed. And this QL was, if I remember correctly, was scaled with respect to the, well, it was scaled essentially with respect, yeah, here it is. It's similar to the heat releases, was scaled with respect to the unburned enthalpy. So those are scaled quantity. That's the key point here. Now, what this picture tells you is the following. As you increase the heat loss, the propagation speed decreases, as you would expect, of course. But it comes a point where you try to decrease or to increase the heat loss further, there is no solution. In other words, there is no steady flame that can be sustained when the heat loss is bigger than a certain value here. So that point would correspond to what we refer to as extinction. In other words, the flame would no longer be able to propagate steadily in that mixture, okay? What you see from this picture is that the extinction occurs when the propagation speed is approximately 60% from the laminar flame speed. So when it's lowered to about 60%, it's going to extinct. Okay. Here are two examples where this can be, if you like, applied. One of them is the safety lamp, the Davy lamp, if you like, that was used in coal mines for illumination. And one of the things that was used in this lamp is to surround it with metal gauze, which essentially they distribute the heat, and that's essentially the heat loss effect, okay? Without that, of course, the flame could have propagated and caused an explosion in the mine. And the second example, so the extent of the metal gauze is, of course, should be such to cause QL to be larger than the extinction value. Another example is flame propagation in narrow tubes. So if the flame is propagating in a tube of some radius, then the total conductive losses through the wall is proportional to the surface area of the tube, which is 2 pi r multiplied by the length L, whereas the heat loss, it's a volumetric heat loss, which is the total loss divided by the volume, which is pi r squared times L. So QL is inversely proportional to R, right? So a large QL means a very narrow tube. And so in very narrow tube, the flame cannot propagate, and something that we know experimentally, okay? And in fact, that can give you an idea of the quenching distance, the tube size below which a flame cannot propagate, okay, in that tube. So those are related to this description of flame extinction. I want to just show you quickly some calculations that were done for a flame propagating in a tube. And this calculation were done without really fully accounting for thermal expansion. In other words, we have used so-called the constant density approximation. And here are the results. They were done for different tube thicknesses. In other words, the radius of the tube is changing, or the size of, actually it was not a tube, it was done in a channel, so it's the thickness of the channel. So delta is, let me see, delta is defined here. So delta is the measure of the channel width in terms of the flame thickness. So a larger delta is it's a wider tube. So what you see here is the following. In wide tubes, delta 20 compared to this, right, so a wide tube, If K is 0, K was the coefficient in front of on the heat loss if you assume conductive heat loss. So it's a heat loss parameter. So when K equal to 0, you would obtain a planar flame, as you would expect, propagating at a speed 1. And that's what you get here. Okay, so you get the flame is planar. What you see here, by the way, those curves on the left are reaction rate contour. In other words, contour that have the same value of the reaction rate, omega. Those are not asymptotic solutions. Those are numerically computed solution with finite rate chemistry, but with one-step chemistry or one-step reaction. And the graph on the right are isotherms, right? They show you curves of constant temperature. And so we are about the time to, what is it? 5:30. Okay, I'll finish soon. So this is for the adiabatic case. Now, as you increase the heat loss coefficient, then the flame curve. By the way, this is half of the channel. So when you see a curve here, there's another counterpart below it. And when you keep on increasing K, the flame will curve, and you can actually reach all the way K infinity. In other words, K infinity will correspond to the walls being held at the cold temperature, okay? So in fact, you will always, in a wide channel, you will always have a flame, except that eventually when the heat loss is large, the flame will not extend all the way to the end of the tube, to the walls. There will be what we call a dead space, okay? And the dead space turn out to be a factor times the flame thickness, which is what you also observe experimentally. However, in narrow channel, which is delta equal to 13, when you, in a adiabatic case, again, you get a planar flame. As you increase K, the flame will curve and will be extended all the way to the end of the channel. But as you increase the heat loss above a certain value, the flame will totally extinguish, okay? So this is the extent that we can calculate. If K was larger than this value, you'll have total extinction. And all these results are put in this graph, in fact. So now it's the propagation speed as a function of heat loss in this channel. So the delta small are the narrow channel. Note that all the narrow channel, the extinction point is very close to 0.6, as in the theory, okay? In other words, the propagation speed reach about 60% of the laminar flame speed, the flame is extinguished. But in the case of wider channel, well, you can increase the heat loss as you wish, and the flame will keep propagating in that channel. Of course, it will not cover the whole extent of the channel, but will be only more in the center of the channel, as you would expect. What is it? Oh, this is just what I just told you. Total extinction narrow channel, of which smaller than approximately 15 LF, okay? And the quenching diameter is approximately 15, the flame thickness. Only partial extinction occur in wider channel, but total extinction occur in narrow channel, and calculation show that the dead space approximately 6 times the flame thickness. I think that's about it. Because of the time, I'll stop here. I will catch up tomorrow on this part of ignition.